Hello, this is the solutions in video form for calculus homework number 37. So we have all of these problems from the textbook. And with the first three problems, 5, 6, and 8, we're just giving the signs for the first and second derivatives for each of these following functions that are given. So it's specified that each derivative is either positive everywhere, 0 everywhere, or negative everywhere. So let's take a look at number 5. So we have a function that is decreasing. So f of x is decreasing. Well, what does this mean for us? It means then that the first derivative has to be less than 0. So it's negative everywhere here. Now, let's talk about how the first derivative changes. So the slope is negative the entire time, but it is a constant slope, right? It is always the same slope value. So that means that f prime of x does not change. And so because it doesn't change, that means that there's no rate of change. So my second derivative has to be equal to 0 everywhere. For my second problem, number 6, I'm going to zoom in for a moment. We have f of x, and we can see that it's going down from left to right. So f of x is decreasing over this entire interval. And so that implies that the slope is negative the entire time. So our f prime of x is less than 0. It's negative. Now, how does f prime of x change from left to right? So f prime of x starts really negative. So it's very negative over here. And it becomes more and more positive, right? So it's getting closer to 0 as we go left to right. So that means that if I go from negative to 0, my f prime of x is increasing. So what does this tell us? This tells us that f double prime of x is positive because our first derivative is increasing over time. Now finally, for number 8, I again have a situation where my function f of x is decreasing, right? I start at some value and I go down from there. So my f of x is decreasing. So that again tells me that my f prime of x, my slope, is negative. Now the question is, how does f prime of x change? So my slope starts close to 0 and it becomes more negative over time. Or you could say closer to a very negative number. So because my f prime of x, is decreasing, that means that my second derivative has to be negative as well. For question number 11, we are asked, does this derivative appear to be positive or negative over the given interval? And explain it. And does the second derivative appear to be positive or negative over the interval? And explain that. So in both cases, we are explaining our answers. So for question part A, we're going to say, is the derivative, so the first derivative, positive or negative? So looking at this, does s of t increase or decrease? So does s of t increase or decrease? So if I look at this, as time goes on, my s of t gets larger and larger. So s of t increases. Therefore, my first derivative, so actually I'm going to write in Leibniz notation, ds dt is positive. I'm increasing over this entire interval. Now for part B, we want to know, does the second derivative appear to be positive or negative? So the question is, how does the relative rate of change? Or sorry, how does the relative, I'm going to go ahead and write it all out, relative rate of change change. So we have two changes in a row. So here, my difference is plus 2, then I have plus 3, then plus 3 again, then plus 11, then plus 24. So it seems like this rate is essentially increasing. So keep in mind, it does say appear. So even though there's a case where we have plus 3 and then plus 3, that's probably just rounded somehow. So our relative rate of change is increasing over this time interval. Therefore, we know that our second derivative, so d squared s dt squared, is also positive because that relative rate of change is increasing. For question number 17, we're doing two things. So for part A, we're estimating the intervals on which the derivative is positive and when it is negative. So we're looking at just the first derivative here. So our first derivative is just the slope. So if we look at this function, we have an increase in our function all the way up to this point right here. Put a line. And so at this point, our slope goes through 0. So we have a positive slope up until this point, at which point it's 0. And then it is a negative slope, and then it appears to get closer and closer to 0. So we're not quite sure it actually gets there, but it looks like it gets closer and closer to a slope of 0. So for A, our derivative is positive for the interval. So let's say positive, actually, so this is first derivative. So we'll say df dt is positive for our interval from negative infinity to, this is approximately negative 0.5. And df dt is negative for negative 0.5 pretty much to positive infinity. So we're not sure that it actually gets to 0, so we're going to assume that it's like a horizontal asymptote. Now for part B, we have a second derivative that we need to worry about. So the second derivative, is it positive or negative? So the second derivative has to do with concavity. So just looking at our function, we are concave down, right? Our graph is pointing or curving downward for this entire interval up until somewhere in this range. So somewhere over here, it flips from being concave down to concave up. So you can just use your best guess. I'll say that it's about right here when it starts to switch to being concave up. So at about this location is where it switches to being concave up. So it's down up until here, and then concave up for the remainder. So my second derivative then, so d squared f dt squared, is going to be positive for the interval from 0.5 to positive infinity. And d squared f dt squared will be negative for the interval from negative infinity up to about positive 0.5. For question number 19, we have a little bit of a puzzle going on. We have a situation where we have a graph with 4 points, A, B, C, and D, and we have some clues talking about the derivatives. So it says exactly 2 of the labeled points, the first derivative is 0. The second derivative is not 0 at any of these points. And so on a copy of the table, give the signs, so this is our copy, give the signs of the function, the derivative, and the second derivative at each of the points. So let's start at A. Actually, let's start at A. So A appears to be below the horizontal axis, so our function value is going to be negative. Actually, let's use it slightly thicker. It's going to be negative. Then, our first derivative could be a situation where the first derivative is 0. So it looks like this is where our function turns around. So let's go ahead and say that that is the location where our first derivative is 0. And then finally, for our second derivative, we see that this portion seems to be concave up. So our second derivative has to be positive. Next, for part B, this also appears to be a location where our first derivative is 0, because this is where our function turns around. So our function is very obviously positive at this location. It's above the horizontal axis. And our second derivative, this appears to be on a section where we are concave down, so our second derivative is negative. For part C, again, our function appears to be positive. We're above the x-axis, or the horizontal axis. Our first derivative, our function is going down, so our slope is negative, so our first derivative has to be negative. And then our second derivative, well, this appears to be to the left of some kind of inflection point. So if we have an inflection point somewhere in the middle here of this section, then this section right here is where we are concave down still. So our second derivative is going to be negative. And finally, for D, we appear to be again below the horizontal axis, so our function is negative, or our value is negative at this point. Our first derivative, our slope, appears to be positive, and we are also in a section that appears to be concave up, so our second derivative is also positive. For question 22, we're asked to sketch a graph with certain specifications for our first and second derivatives, as well as the value for our function. So I'm going to start just by sketching a set of axes. I'm going to sketch them nice and big, although apparently not very straight, so that I can sketch anywhere on them. So here are our sets of axes. Now, when we're sketching our function, we want to sketch a function so that f of 2 is equal to 5. So somewhere over here at 2, so let's say this right here is 2, we have a function value that is positive 5. So here is our function at f of 2. This is equal to 5. So at f of 2, or at x equals 2, our first derivative is 1/2. So at this point we have a slope that is essentially positive, although it's not very steep. So we can sketch like a little bit of a tangent line right through this point. Then we also have a fact that our second derivative is also positive, which means that our function has to be concave up. So our slope is going to be changing, and so our function has to look something like this. So it's curving up. So let's make this a little bit more obvious. So here's my point, and I have something, and it doesn't matter exactly where this is, that is curving up. So I'm concave up, I have a positive slope. And my function could look something like this. You may have something slightly different. Question 23, we're given some information similar to what we had for question number 22. So I'm going to start by just sketching a little bit of a graph for this information. So I have my axes, and I have f of 5 this time. And I know that at 5, my function has a value of 20. So I have something where this is a point of my function. Now, f prime of 5 is positive 2, so I have a positive slope. Zoom up here. And our second derivative is negative, so I'm concave down to the right of this. And so that's for x greater than or equal to 5. So what does this mean for my actual function? So I have a positive slope, but my function is concave down for x values greater than 5. So I have something that I'm increasing, but I'm curving downward from this point. So it looks something like this. So the question is, which of the following are possible values for f of 7? So somewhere over here, so anywhere along this function, could be f of 7. We're not sure. So which of these are possible and which are impossible? So if I'm concave down, that means that f prime, so I'm going to write this in a different color. So my f prime must be decreasing. So if this f prime is positive 2, then over here, my f prime has to be less than 2. So what does this tell us? Well, after one set of motion here, our function has to have a value that is lower than 22. So this right here has to be, so f of 6 has to be less than 22. Because if my slope, again, at f of 5 is 2, that means my slope is getting lower from that point, so I can't have gone up more than 2 from 5 to 6. So at x equals 7, so this is just arbitrary, this right here has to be less than 24. Because again, I cannot go up more than 2 from 6 to 7. So which of these are possible or which of these are impossible? Well, if f of 7 cannot be greater than 24, that means that A is out and B is out. So only C is a possible value for f of 7. These two are impossible. And again, the reason I know that is because my f double prime is negative, so my slope has to decrease. Since my slope started at 2 at this point, my slope has to be less than 2 everywhere to the right of that. For question number 28, we have a set of graphs. So we have 4 graphs here. And they show the position of a particle moving as a function of time from 0 to 5 seconds. The vertical scales are the same, so our up and down is the same. During this time interval, which particle has a constant velocity, initial average velocity, and then we talk about acceleration. So let's do a quick review of what you have seen previously in this class. First off, velocity as a function of time is the first derivative, or the rate of change, of position with respect to time. So we can write that as x prime of t or dx dt or dx of t dt. Either way is fine. Similarly, acceleration is the rate of change of velocity or v prime of t or dv of t dt. Now, since v of t is already the first derivative of position with respect to time, we can actually say that this is the same as d squared x dt squared, or the second derivative of position. So knowing this information, we can go in and say, all right, this graph will have a constant velocity if dx dt is equal to a constant. So which of these has a first derivative that is constant? Well, this one, the slope changes. This one, the slope changes. Number 3, the slope changes. So number 4 is the only one where there is constant velocity. So I'll put it both up here and I'll put it down here. So A applies to number 4. I'll write it over here. Now, which has the greatest initial velocity? So here we want to know about dx dt at time 0. So we want x prime of 0 is the greatest. So if I look at this, the first graph has a pretty positive slope. The second graph has a positive slope, but it's not as steep as the first graph. And then the third graph has a very steep slope at x equals, or t equals 0. Then our third graph has a negative slope, so that's definitely not the highest. So since this pink line here represents my x prime of 0, out of these three, it appears that number 3 has the largest initial slope. So B applies to number 3. Now, which has the greatest average velocity? So here we're going to have to actually look back at a definition. So if you recall, average velocity is just going to be the total change in position over the total time. So if I look at the change in position for number 1, I start at 0 and I end at 0. So my average velocity is just 0 over 5. So that's 0. For number 2, we have a very positive average velocity. So average here is very positive. So since these are the same scale, we can say, okay, what about from here to here? Well, this is going to be less than number 2. So this is less than V average for number 2. Then finally for this, our V average is negative, so that is not going to be our greatest average velocity. So out of these three, it appears that number 2 is the one with the greatest average velocity. So, moving on. D, which one has 0 average velocity? Well, since we've already looked through our average velocities, it appears that number 1 has an average velocity of 0 because there's no overall change in position. So D applies to number 1. Now, which has 0 acceleration? So for 0 acceleration to be true, actually let's go ahead and use a different color for this. For 0 acceleration to be true, that would mean that we have a second derivative that is 0. So d squared x dt squared equals 0. Or, what does that mean? That means no curvature, no concavity. So which of these has no concavity? Well, that is number 4. So E applies to number 4. And finally, which one has a positive acceleration throughout? So d squared x dt squared is positive always. So for number 1, should have changed colors. So for number 1, we have concave down and then concave up. So our concavity or our second derivative changes, so it's not number 1. For number 2, it appears that our concavity is always up. So F applies to number 2. For number 3, our concavity is always down. So our second derivative is negative. And then for number 4, our second derivative is 0. So the only one that this works for is number 2. So taking all of this in, the point of this question is to relate our first and second derivatives back to how we modeled the motion of a particle. So again, velocity is the first derivative of position with respect to time, and acceleration is the first derivative of velocity with respect to time, or the second derivative of position.